You know the names, Llama 4, GPT-4, Grok. They're basically the titans of AI right now. But they all share a secret weapon. It's this one architectural trick that, until pretty recently, was one of the industry's best-kept secrets. So today, we're going to pull back the curtain on that very secret, the mixture of experts.
And it really all boils down to this one question. For years, the only way to make AI smarter was just to make it bigger. But that creates a massive problem, right? How do you get all that brain power without the model becoming painfully slow and wildly expensive? That's the puzzle we are going to solve today.
To really get why the solution is so clever, we first have to talk about the problem it solves. And in the world of large language models, it's a numbers game. Specifically, this huge scaling dilemma that comes with having billions and billions of parameters.
So this really lays out the core tension in AI development. On one side, you want more parameters. Think of them as all the little knobs and dials the model has. More of them means better performance, for sure. The model can memorize more, it can understand more complex stuff. But here's the catch. Every single one of those parameters has to fire up for every single calculation. That requires a ridiculous amount of computation, which we measure in flops, and it makes these giant models just unbelievably slow and expensive to run. It was a total bottleneck.
Okay, so the challenge was crystal clear. How do you get all the benefits of a massive model without that crippling cost? What if you could get all that knowledge for a fraction of the price? Well, that's exactly the promise of an architecture some people have called a free lunch.
Okay, so first things first, the name mixture of experts is super misleading. Seriously, it makes you think of a team of little specialists, like one for coding, one for history, one for poetry. That is not what's happening here. The reality is actually much simpler and honestly a lot more clever. An MOE model just takes one huge part of the network and smashes it into a bunch of smaller pieces, which we call experts. Then this little traffic cop, a router, looks at whatever you ask it to do and only wakes up a couple of those experts to actually handle it. And this visual just shows the difference perfectly. A traditional dense model, it's like one giant factory. Every single piece of data, every token, has to go through the entire assembly line. It's powerful, yeah, but wildly inefficient. An MOE model, though, is totally different. It's more like a central dispatcher with hundreds of little specialized workshops. When a job comes in, the dispatcher just goes, okay, this one just needs workshop number 7 and workshop number 52. All the other workshops, they stay dark, saving a ton of energy.
And that, right there, is the magic of MOE. This is the big aha moment. You get a model with a truly vast number of parameters, we're talking trillions, but the actual computation, the flops, stays low. Why? Because you're only ever using a tiny slice of the total model at any given time. You get more knowledge, but for the same cost.
And hey, this isn't just a theory. The results speak for themselves. This chart shows that if you take the exact same amount of compute power, the same training budget, MOE models always get a lower training loss. And all lower loss means is that the model is better at its job. It's literally getting smarter, faster, for the exact same amount of work. That is a massive advantage.
So this all seems like a no-brainer, right? Which kind of begs the question, if this is so great, why are we only hearing about it now? Well, it turns out that for years, this so-called free lunch came with a very tricky catch.
The idea itself has actually been floating around for a while, but getting it to work in the real world was incredibly hard. There was this one huge roadblock that kept tripping everyone up, a problem that turned these smart, efficient models into lopsided, inefficient messes.
And that problem is called expert collapse. See, during training, the router would basically get lazy. It would find one expert that was just kind of good at most things and then just start sending all the work there. And you end up with what you see here. One expert is doing 92% of the work, while all the others are just sitting there completely wasted. It's like building a supercomputer and then only using one of the cores.
So why does that even happen? Well, think about it like this. AI models learn best when they can make tiny, gradual adjustments. It's a smooth process. But the router's decision isn't smooth at all. It's a hard winner-take-all choice. Send it to expert A or send it to expert B. And because the model struggles to learn how to balance these hard choices, it just gets stuck in a rut. It picks the first good enough option it finds and then never bothers to explore any of the others. So how'd they fix this? With a surprisingly simple but really elegant trick. The goal was to get to this ideal state, a perfectly balanced workload where every single expert is contributing and the whole system is firing on all cylinders. They came up with something called a balancing loss. You can basically think of it like a penalty flag in football.
During training, this loss function just watches the router. If it sees the router starting to favor one expert way too much, it throws a flag and says, hey, spread the work around, you're being penalized for not using all your resources. It's just a little nudge, but it was the key that finally unlocked the insane power of MOE at a massive scale.
And once that expert collapse problem was solved, MOE went from being this niche academic idea to being the secret sauce inside pretty much every single major AI model out there.
And I mean, you can see its impact everywhere. Just look at this lineup. Meta's Llama 4, Mistral's Mixtral, xAI's Grok, DeepSeek, they all use a mixture of experts architecture. You see the pattern, right? A huge number of total experts or parameters, but only a tiny fraction of them are active at any one time. This is it. This is the blueprint for building state-of-the-art AI right now.
And the benefits are more than just efficiency. Since the model is already broken into all these little pieces, it's super easy to just put different experts on different GPUs. That makes training these truly enormous models way more manageable. But it also has some weird side effects. Sometimes an expert gets overloaded and has to drop a piece of info. That's actually why you might get a slightly different answer to the same prompt even if you turn the model's randomness or its temperature all the way down to 0. It's a small quirk, but a small price to pay for this massive leap in power.
So let's wrap this up. Mixture of experts solved this huge, fundamental scaling problem. It gave us that free lunch by separating a model's knowledge from its computational cost. It's the silent workhorse that made today's AI giants possible, which of course leaves us with one last really exciting question to think about. If MOE was hiding in plain sight for all those years, what's the next big architectural trick that we're all missing right now?